Yeah, so my name's Will. I've been around Protocol Labs for about 4 years, and this is a talk looking at what we actually mean when we talk about decentralized networks and trying to get into some of the opportunities for cross-layer optimization and some of the trade-offs that are there. Just in terms of what we're going to talk about over the next 20, 30 minutes. I'll try and talk about some of the trade-offs and where things are with networking right now, and sort of like the main things we get when we are talking about, oh, I want a peer-to-peer or a decentralized network, and then spend probably the bulk of the time talking about a couple case studies in ways that you can take advantage of what you actually have already compromised on in order to make the type of system that you end up with. There are several decentralized networking library stacks, right? Ethereum has a mix of dev-P2P and lib-P2P. I think Parity is on a lib-P2P stack. There's a set that custom roll, but they end up using sort of a bunch of these same core things that they're doing. There's some set of things around how do you actually get connected and maintain a connectivity mesh. There's a set of searching and finding either content or other nodes that you need to talk to once you are connected. And then there's some consensus layer that typically is getting built above that to have some state of we all agree on something that's going to then evolve. You've got some transport and NAT traversal and a set of these underlying networking things as well for how do you actually make those connections, keep them working despite nodes moving, nodes going offline, et cetera. And I think the thing that's interesting to note is you've got this ideal of decentralized, fully homogeneous, all of these nodes are the same. And I don't think anyone ever gets there, right? That's this aspirational, very far thing that we are, in every case, making some amount of compromises. And so I think we don't often think about what we've already made compromises on, and then how to do as good as we can having made those compromises. To make that point, let's talk about how we're going to actually start that connection, right? I think most pieces of software have a set of hard-coded bootstrap nodes that are what the piece of software when it starts up connects to initially. And so there's this trust in the authority of the developers to then delegate what are those points of connection. And then you've got already sort of a choice that you need to make, which is, are you caring about sort of this predictability versus are you going to push more towards that peer-to-peer thing and give up some control? So you may just have a core set of bootstrap nodes. That's sort of the first thing that any lib-P2P or general peer-to-peer networking stack has. As you see things that need additional sort of how do we deal with stuff getting blocked or whatever and the software not being easily upgradable, maybe you'll have some statement of the current set of bootstraps that gets signed, and you'll also distribute a key and allow the network to have sort of a consensus of an updated set of bootstraps. So something like Tor does this, where there's this directory authority list that can update sort of nodes that you get connected to, and you use that to sort of stay up to date. Where you're not directly trusting your bootstraps, you're trusting something that is a delegate of the developers. On the other side, there's a lot of things that will go with something easier, where they'll go to just a centralized website and pull the current list. And it's as long as that works, you've fallen back to DNS infrastructure, but that's a very predictable thing that lets you rotate those points of connection. But either way, right? This is saying there is a heterogeneous thing. There's we're trusting a centralized development entity to decide on who I connect to in order to get into this peer-to-peer network. And maybe I get to keep being connected to the peers that I saw recently. That's better than not having that. But we have very few networks where I get the piece of software, I have to find my friends, and there's no based existing trust. The second example of this is the search of how do I find either a specific peer or a piece of content or something? How do I actually send messages through this network? And we've got like a trade-off here that a lot of these libraries are making for us, where on one side you want to sort of find content quickly, and so you'll use stuff like your existing connected peers. Maybe you'll keep a local reputation of like, oh, this peer has given me a lot of stuff. I'm going to start by going to that super node before I go to some random node. Or maybe you are doing a full search with something like a DHT. And you've got this, again, a trade-off that you're making in terms of, are you going to stick with these sort of like peer-to-peer principles versus are you going to take shortcuts? Are you going to compromise on a homogeneous network in the favor of like, well, okay, I'm doing something that's not as predictable. It's taking a shortcut in some sense, but it's going to work better in practice. And then we also, I think, face this same sort of space, design space in consensus. I'm going to speak a little less about this because there's just so much stuff, especially in blockchain, that has gone with consensus. But I think you have both this axis of like homogeneous versus structured, of like, are you going to go full Byzantine fault tolerance? Are you going to put some effort into having a limited, more trusted set of validators that then are able to do that faster? We've seen that debate raging across the blockchain space. You've got this question of like, how efficient are you going to be as well, right? Of like, you can get to an efficient consensus by just trusting someone more, or you're going to go to this full peer-to-peer thing that's less efficient. So this chart of like where you are, there's some curve of optimal that we're discovering over time. Right. So like you could send a message by having every node just flood messages through. We have a set of gossip or flood protocols that do this that are fairly homogeneous. Any node can do that without much heterogeneity, but they're much less efficient than the structured consensus things. So what do we gain from these compromises? And to sort of address that and talk about it a little bit, I'm going to give two examples at different layers. The first is an ISP that I've helped with called Emerald Onion. We set it up to provide Tor exit service. So it's a nonprofit entity that was just what are the economics of just providing free bandwidth? And it's been an interesting project to then see what the realities of some of that actual infrastructure of networking looks like, and how you can then use that as a stepping stone for what we actually are ending up with in higher level peer-to-peer networks. And the second one is IPNI, which is a project that came out of Protocol Labs and is looking at how to better make use of the compromises we already have in the DHT. So this is the search problem. And as you get the heterogeneity, can you use that to get something that's faster and gives you something closer to what you're after? So let me start with a little bit of discussion of Emerald Onion. So we started this 7 or 8 years ago. It's a nonprofit ISP, 501c3 in the US that started in Seattle, and that gave it its name. And one of the things that you see pretty early is that your efficiency of network is not a linear thing. So as you go from asking for a gigabit connection in a data center to a 10 gigabit to a 100 gigabit, those prices aren't like 10x and 100x. That you can say, oh, I want 100 gigs of transit, and that's really only like twice the cost of 10 gigs of transit-ish, depending on where you are. But the costs really are not linear, and there is, in your networking layer, a strong incentive already to centralize because of those nonlinear costs. So as you talk about, oh, we're going to be efficient with all of our small nodes in people's houses, that is going to be extremely more expensive given the economics of the layer underneath you. And so that leads you then to this question of like, okay, how do you take advantage of that? What do you do given the fact that your network is going to just be very, very cheap if you can have these locations where you're paying for larger amounts? Right now, We are in 3 locations. We've got around 30 gigabits of uplink transit, and it's costing less than $1,000 a month for everything. And by everything, I mean space, power, and network. So that's like the expenditure run rate. And so that's like, I don't know if this is surprising. I think this is a useful data point to share because it is probably less than what you would find as a commercial quote for data center space. By probably quite a bit. It depends a little bit on region. This is like less totally shocking to someone who's got ISPs in North America or Europe, but this is still, I think, pretty good compared to what you would find in getting quotes. In particular, as you start looking at like a full rack, you'll be looking at like, and that's 42 spaces of servers. That's already like going to commercially quote you at orders of $1,000 a month. And we've got a few of those, one in each of the locations. And then the interesting thing, you get a lot out of being nonprofit. People like to sort of like, it is easy for other companies that are in data centers to say, oh, we have extra bandwidth. We can just sort of like donate that to some nonprofit. So you'll find other ISPs in the data center who will give you free additional transit. And that's a nice feature that you learn about once you have that. Once you send out the email that announces to the Internet Exchange, the IXP, we've peered. You'll have typically a relatively high link of bandwidth to your data center, so to the other ISPs that are located in the same physical building. And then what is your expensive cost, relatively, is getting out of the data center. But you'll find that there are other ISPs in that data center who are able to say, I have spare capacity I'm paying for on the way out. You can use some of mine. I'll let you route some of your traffic through me. And so even if you're paying for only 1 gigabit, you can get up to 10 gigabit or whatever just through free additions from some of these other ISPs that have spare capacity and who are happy to give it to, in particular, nonprofits because they're not using it. So there's a bunch of interesting economics that come into play where there's just a ton of slack at that level below that you can take advantage of. The interesting thing then that we get to make use of, that's sort of like the exciting part of Emerald Onion for me, is looking at a very high-level threat model. When you talk about something like Tor or privacy preserving systems, the threat model is someone is like watching these nodes, and some government or NSA-like adversary is trying to correlate who's sending traffic in and then where they're going, and like can they de-anonymize. And that's this very nebulous attack in some form, right? Like, how do you actually identify that? What's going on? The interesting thing is that in practice, the expectation is that most of that monitoring happens at country borders. That's where there's both centralization, there's very few undersea cables and so forth, and connectivity points between countries versus in each city. And also, the laws make it easier for wiretaps and so forth to happen at those cross-country borders. And so one of the things we can do, because transit gets cheap, is we can have a point of presence in Europe, and all of the traffic that comes into us will come into our network at our European server, and we can then send an additional constant bitrate encryption pipe back to our points of presence in the US. And so we can take the traffic that would logically be in a single location, and from the point of the distributed network above us, looks like it's in one location, and we can actually make the wire have a different property than would be expected from the threat model, and a better one. And it doesn't cost us much. And that's this interesting cross-layer application that is a thing that would be very hard to model in your distributed system if you're thinking about it at that overlay level, but you can actually make progress on once you go down to a networking level. So I think that's like this interesting takeaway, which is we often are not going down to the wires, either for the prices or for the actual behavior of them. But when we do, we can do a lot better. Okay. The second one I want to talk about is IPNI. And this was a reaction to wanting to, well, it's a reaction of a few things. The first one was, how do we make something that competes with a normal web experience? You want to find content on IPFS or just in general this sort of distributed web. Right now you go to a DHT and there's limitations of how well you can get a DHT experience to compare to going to Cloudflare, right? The DHT is going to have a logarithmic, but it's still going to have multiple nodes that are somewhere in the world that you have to connect to actually get to who has your content. And so you've already sort of lost your speed comparison, not even if those are great nodes. The fact that I first have to go to somewhere and then I have to go to someone who happens to be in Europe means I've lost some hundreds of milliseconds, and this isn't going to be something that's competitive, especially as whatever your content is grows. Like if you get to popularity, you're going to have more nodes in your DHT, and you're going to end up with less predictability. So just that sense of, okay, this isn't going to work with scale, and the design is not going to give us retrieval characteristics that we want, but we want to still be distributed. What do we do? And so the IPNI response is, well, okay, the lookup table, what we're putting in a DHT, be it BitTorrent, be it IPFS, it's not that big. It's like a hash to an IP address. This isn't like an actually scary amount of data. And since we're trying to say that these homogeneous nodes in a DHT world are people's desktop computers, each of those computers can't store that much. So even if you just had a supernode that stored everything, that's pretty doable. So let's build some supernodes that just have a hash table instead of a distributed hash table. And then let's figure out what it means to just keep that a distributed system, right? So that's where we ended up. It has a set of servers. I think the internals don't matter so much, but let's get a big node that just is the hash table, and let's get a few of them, and let's figure out what it means to federate these. If you want to keep a full copy, you probably want it at least eventually consistent. And what levels of consistency do you need to not have to trust or care about the availability of any given one? And at that point, are you good enough? We also were starting to worry about Filecoin pushing all of its data into IPFS and overwhelming the DHT, so we need to care about these nodes that just had a lot of content on them, where with something like a BitTorrent or IPFS or just general Kademlia DHT, your process for eviction and for keeping content fresh is you republish every day or every N hours or whatever. But as you have a lot of content, that gets to be pretty expensive. You'd like to say, I've still got the same stuff I told you about last time, rather than having to say what all of that stuff is each time. And so figuring out what that means was sort of the second part of that change in design. Was we're going to make sure you're still online. We can build some sort of fraud-proof things where if people try and get your stuff and can't, that means you're not telling us the truth and we're going to get mad at you. But in general, we're going to trust a little bit more until we hear otherwise, that you have what you say you have. So we've been running for a couple years without downtime. The federation mode seems to not be like an availability issue. We've got something like 60 terabytes of hashes to IP addresses as that primary hash table that's being replicated. And we've got the P95, so 95 out of your 100 queries will get responded to in less than 100 milliseconds. So we're able to, I think we'd like that to go down to 30 milliseconds or something like that. That's going to take some other caching layer that's like city level rather than these full tables that are probably regional level. But that's the regional level performance is something that we can work with. And the thought here is both moving to something that's federated is easier to reason about, right? Like the DHT is a complicated system that I think has taken several teams quite a bit of time to try and understand things getting lost, if they're really getting the performance they expect. Whereas having something where you can reason about a full instance on one machine has much lower barrier of entry, and so you can have a lot more developers make progress on that, which is a nice sort of additional feature in thinking about this. And the compromise, right, is like this is much more heterogeneous. Like not anyone can spin up a $5,000 to $10,000 server to be a full replica. And that most of the cost there is storage. It is 60 terabytes of like fast NVMe SSDs. And you just go on eBay and get them mostly new, and like they're not that expensive, but like that is probably $3,000 to $5,000 of hard drives. If you want your key value store to be able to get through that much in a good response times. And that's not something that someone's going to run on their desktop. So you've limited your pool a lot, and now you suddenly go into the same conversation that a bunch of blockchains did about, okay, does that mean we have to incentivize operators? Right now, we're still operating in sort of a public good, general, like, this is an overall cost for the service that is small enough that it can be handled by sort of these public goods, general grants, and so forth. And the nice thing is we think that the value that it has to any of these distributed networks is sufficiently high that that will scale with growth and costs. That in the same way that no one's really, like, the cost of running this sort of infrastructure is going to be less than the cost of funding a DHT team to build and maintain your DHT as you scale. That it basically is a sustainable type of thing, is my hypothesis at least. Things we're working on is that this really is a generalized key value store. It's not, like, we're using it right now in a couple cases of what IPFS Filecoin used for searches, but it is a key value store, right? And so there's things like Ethereum attestation service, and just generally this is that search in a distributed but now federated network that you can move towards while still having, okay, I don't have to trust any given participant. I can keep my trust reduction, and I can fall back to a DHT if I need to. And so it's this thought of progressive decentralization that I want to get back to of this general networking world, right? And the key is we've made the compromise of having trust in your bootstrap nodes, of having a heterogeneity already in your consensus or whatever. So if you've made that, take advantage of it. Like, go with something federated. If you've got a path to progressive decentralization, don't forget that. But do the thing that actually works, and you'll end up being able to have a service that gives you much better performance. So don't let that sort of like goal of full peer-to-peer make your lives too miserable when you've already had to compromise it in 3 or 4 other ways. I think that was the core nugget that I wanted to get out there. Happy to answer more questions. I'll be around for a bit, and thank you. Enjoy Sub-0.
Great. That's fantastic stuff. Will Scott, what an interesting perspective. Thanks very much. Do we have any questions from the audience right now? Oh, yeah. Okay. Run. Here we go. Big catch. Oh my gosh. Everybody okay? Everybody okay?
Thank you. Super interesting. Do you, like, my fear is always that, like, when you really get down to it, if you really want to hit the performance people expect, you end up going really close to just back to the same stuff, you know? And I'm curious, like, do you think, where will we discover the ways to actually achieve these efficiencies without huge compromise? And I personally think sometimes that we have to be down at the network wire level, but yeah.
I mean, I think the interesting thing here is what is the forcing function the other way. Once you're seeing an adversary or some other thing that is the counterpoint, that's when this develops naturally, right? If you are some external service that needs to work in a country that doesn't want it to, suddenly you've got a motivation and there's a structure and there's constraints to build something that meets that. I think in absence of that pushback, be it regulatory, be it something else, you're going to see things sort of weaken and move towards what's easiest, and that's just expected.
Very interesting perspective on internet service providers. I really loved it, and especially like the ability to make them public and free. And actually, it got me thinking that it could be possible to provide these services maybe to IT professionals, so they can have their own like home server or like home lab, whatever, and they would run what we call now the pin at home, so they could run the either full node or the not decentralized like archive of a blockchain. And the second thought from it was like, why wouldn't we make it like target specifically those people who are for like setting up their home labs and maintaining it on a more professional level, maybe even kind of incentivize them doing that, maybe even paying for that, like some fee, whatever, like network fee, this kind of stuff. But also from the other side, democratizing the hardware requirements. So for instance, not having the hardware requirement of full archive node, which is very expensive, especially for the home, electricity prices and like network throughput and everything. There could be an additional, not very complex system to like algorithm to structure the periodic archive node, so it would save not every block, but say every second, every third, whatever, and their neighbor would save every other second.
Yeah, I mean, I think both of those points are valid, and I think the interesting thing that maybe you'll take away from the ISP discussion here is that you can get potentially even bigger bang for your buck by going a step up from the home lab to the ISP operator. That there's some technician in pretty much every data center who just has a few spare racks and may well be able to slot in very sizable nodes if they think it's a cool idea. Mm-hmm. I think we saw that in early days of crypto. I think we continue to see that as like some of the like strongest IPFS nodes are just some guy who's got an extra rack in a data center that's, from their perspective as a larger ISP, Slack, that it's free. And so if this seems like a cool idea and is easy to set up, there is a market there that can really get you a long ways.
Yeah.
All right. Will, thanks very much for coming on and sharing these ideas. We really appreciate it.